31 شهر اردیبهشت هست. آخرین روز ماه اردیبهشت سال 1401 جلسه میکنم 12 درس زمین آمار هست که در خدمت عزیزان هست. Finally, we reach a point where we could address estimation in geostatistics. As I said, I would like to invite you to criticize this way of teaching geostatistics. It's very different from various textbooks that you have at your disposal. Instead of touching on various in a fragmented manner, we try to introduce a framework. At the very beginning, we have to state our problem as clearly as possible, and that is general problem statement given. A single partial realization of a random function then we are asked to estimate the attribute under consideration at a point which is not sampled. Please pay attention. We have to qualify our given information. We have to qualify what we are looking for. And then as soon as we have a very clear, transparent aspect of our data, then we are ready to go for estimation. You may want to appreciate the idea of why I am claiming that this way of teaching geostatistics is very different from what you have in various textbooks. That is the general problem statement for univariate treating, trying to estimate the attribute under consideration using the same attribute. In fact, what we are given is a random function, but not a closed form function for a random function, just like what we have in our previous lecture, where we can easily compute theoretical value using closed form function of the random function. But because we have a single partial realization of a random function, then it is not possible to obtain, to compute the theoretical value. At most, we can compute experimental value. But before trying to go for either experimental diagram or theoretical diagram or whatever you have in your mind, we have to make a decision on whether the expected value of y is given or not. That is the trend, the drift, the mean function is given to us or not. It really doesn't matter whether it is a function of spatial location or not. It could be a function of spatial location, and it could be the case that you are given variable mean. You have known variable mean. Therefore, that is one aspect of the new approach where at the very beginning, you have to specify whether the expected value of the attribute under consideration is given or not. For this first scenario, we will assume that the expected value of the attribute under consideration at the generic point S, please pay attention, this generic point S could be any point in your study area, is independent of spatial location and it is given. As soon as you decide on these two information, given and constant value of the mean function, then you have to make a decision on whether your variance is independent of spatial location or not. We are not talking about whether the variance is given or not. It has nothing to do with estimation. Therefore, variance of the attribute under consideration would be constant or variable. For this case, we will assume that the variance of your random variable is independent of spatial location. Please pay attention, this A and B concern with what you have here. Another aspect of these given information concern with support size. You have to make it clear the support size for your observation. You have two possibilities. Your support size for observation could be pointwise or locwise. As you are coming from groundwater hydrology, or better to say hydrology in general, almost every textbook written on hydrology will assume that precipitation, evaporation, temperature, soil moisture, radiation, you name it, is pointwise. You are monitoring the attribute under consideration at a point in a space. Therefore, pointwise observation. I have yet to see, please pay attention, I have yet to see if any textbook written on geostatistics where it assumes that the attribute under consideration is given in clockwise manner. What does that mean? Almost every textbook written on geostatistics will assume that the attribute under consideration is given in pointwise manner. The support size for observation point, not clockwise, which means that it seems that in geostatistical literature, they will assume that if your data are raster-based, regularly based, then it makes no sense to go for estimation. And this is not true. In my case, it happened that if the diameter of the laser is less than the diameter of the hole over the surface, then the laser will penetrate into the hole, and then on my digital elevation model, I was getting 999 garbage. Therefore, it means that even out there where we have regular-based data or raster-based data, there is a chance to go for estimation, trying to fill the gap, the garbage data in your data structure. But try to criticize this way of claiming something. Abedin is saying that in conventional literature, you could not find a problem statement where your observation is block-wise as opposed to point-wise. But you can find a variety of problem statement where your observation is point-wise, but you want your estimation to be block-wise. It is possible. And we are going to cover that again. Your estimation is point-wise as well. Point-wise estimation. Which means that the support size for both observation and estimation is point-wise. If your mean is constant, if your variance is constant, then when it comes to either measure of similarity or measure of variability, we have three scenarios for measure of similarity or measure of variability. It really doesn't matter. Your measure of variability could be a function of absolute location, which is considered to be dead end in geostatistics. You can go nowhere if your correlogram or covariance function or variogram function is a function of absolute location. You can go nowhere. Therefore, forget about that. You have two other possibilities. Your measure of similarity or measure of variability is a function of separation vector or separation distance. What I'm going to cover from now on will be applicable to both scenarios. Unfortunately, students would not appreciate this fact that what I'm going to derive today is very applicable to the case where your measure of similarity or measure of variability is a function of separation vector. They will assume that the measure of similarity or measure of variability is a function of separation distance. What I am saying, and you will notice it today, what I'm going to derive is very applicable to both scenarios. Your measure of similarity, your measure of variability could be a function of either separation vector or separation distance. E, measure of similarity, i.e. R or rho. And variability i.e. gamma. Could be a function of separation vector or separation distance. If I write down h, it means separation distance. If I write h with vector on top of it, it means separation vector. If you have a scenario like this, where your mean is constant and given, your variance is constant independent of spatial location, your observation is pointwise, your estimation is pointwise, and either measure of similarity or measure of variability is a function of separation vector or separation distance. In geostatistical jargon terminology, this scenario is called simple glitching. We are going to solve this problem in a systematic way, touching on a number of steps. Step 1. This step might be applicable somewhere and it might not be applicable in some other scenarios. For this scenario, it is very applicable. What is that? If m is given to us, if m is known, then we can switch from y to w. Compute W at SI for all I from 1 to n via W SI is y at SI minus given m. Please pay attention. As soon as m is given, and it really doesn't matter whether m is a function of spatial location or not. You could have a scenario where m is a function of spatial location and it's given to you. This is the trick. This deterministic component of your random function. As soon as you know m, then you can switch from y to w using this relationship. Because y is given, m is there. Step 2. Or better, if we could implement step 1, then we can restate our problem. Given W at SI for all I from 1 to n, then our job is to estimate W at a point which is not sampled. That is the new problem statement. Step 2. In step 2, we have to cast our estimator, W hat. Our estimator can be written as a linear combination of these given Ws. It can be written as I from 1 to n, lambda I, which is a function of S0. If you change the point under consideration, then this coefficient will change, times W as a function of S. That is our estimator. In a discipline so-called linear geostatistic, and it is applicable to almost all numerical method in deterministic approach. Final difference, which is the engine for mod flow, finite element, which is a numerical solver for a number of programs like GeoOffice or whatever program. ANSYS is another program where the engine is finite element. Differential quadrature, method of characteristics. Mrs. Rajab is not method of characteristics of mathematical too, but numerical aspect of method of characteristics. In almost all numerical methods devised to solve a given ODE or PDE, the approximating function or interpolating function or a typical element can be written as a linear combination of nodal values. And you can see here that the estimated value of W can be written as a linear combination of either computed value or observed value. That is step 2. When it comes to step 3, in step 3 you have to cast your residual. And that is where geostatistics depart from least square. In least square, you will define your residual to be the difference between computed value and observed value. But when it comes to geostatistics, you will define your residual to be estimated value minus true value. At this point, in fact, it makes a lot of sense to tell you another things which is quite important. Could it be possible to have these systematic steps in linear or nonlinear regression? Could we have the same systematic procedure to be able to compare and contrast what we have here with least square? If you want to state your problem in least square, I will write it with different color. In your problem statement here, you will say, given xi, yi for all I from 1 to n, which means that you have a table. First column of that table is your independent variable. Second column of that table is your dependent variable. You are given that. And then you are looking for a closed form function between y and x. Find could it be possible to restate this find in another way? Just like what we have here? Yes, why not? We observe x0 and we would like to obtain y at this. See? You are given n observations. At first, we state our question in this way, compute a closed form function relating x to y, and then we want to see what would be the advantage of this closed form function. The advantage of this closed form function is to be able to obtain y given x, just like what we have here. Once again, here we have 2 degrees of freedom. Which mathematical function? Which could submit criteria to obtain this. And then, when it comes to various steps here to solve this problem where you have some familiarity with, you have to play with your given data, map them on your first quadrant, check the mathematical model that you could select in order to find the parameters. And if you want to compare step 2 with what you would have when you want to solve this problem, here the mathematical model is this in geostatistics. A linear relationship between observation and estimation. When it comes to least square, a functional relationship between independent variable and dependent variable is this. Therefore, step 2 is to choose your mathematical model when it comes to solving this red problem. Now, if you want to tell your audience what would be a step 3 in least square, and it is quite important to appreciate this fact. Here, you will define your residual to be estimated value minus true value. When it comes to least square, you will define your residual, your error, to be computed value minus observed value. Can you see the difference? Here in geostatistics, you will define your residual to be estimated value minus true value, which is not accessible, but because you have a stochastic framework for your problem, you can get rid of this dead end where it is not accessible. Here, because you will not define your problem in a stochastic way, in least square, you will define your residual to be computed value minus observed value. And this observation is basically what you have. It is quite important to follow this one-to-one correspondence between what you are doing in geostatistics and what you are doing in this square, to be able to appreciate the difference between the two approaches. When it comes to step 4, By the way, if you even compare your step 3 here with what you have here, here your residual will be a function of spatial location, the point where you want to have an estimation. But when it comes to your residual in this square, your residual in this has nothing to do with spatial location. It is just a function of this I here, which means that every row in your table could have an observation as well as estimation, and you will define your residual to be computed value minus observed value. If your functional relationship connecting y to x is linear, then you will say my computed value is basically axi plus b minus y. This is how you define your computed value. If your mathematical model is power law, then you will define it as axi to the power of b minus y. That is how you define your residual in this square. When it comes to step 4, you have to impose unbiasedness condition on your residual. By unbiasedness condition on residual, because this is a random variable and this is another random variable, therefore if you subtract a random variable from another random variable, you are going to get a new random variable. And by unbiasedness condition, we mean the expected value of R has to be 0. Expected value of residual has to be 0. And I have to put a question mark here, implying that we have to look for a relationship where if we honor that relationship, then the expected value of R is 0. For this case, we will notice that the expected value of R will automatically be satisfied. But in some other scenarios, it is not the case. You have to look for a relationship so that if we honor that relationship, then the expected value of R is 0. How about the counterpart? How about the corresponding idea here? Please pay particular attention to what we argue here and how we are going to satisfy the same idea here. We will try to choose our mathematical model so that the expected value of y is 0 always. What does that mean? If we choose our mathematical model incorrectly, then the expected value of this epsilon is not going to be 0, which means that we are not okay with our mathematical model. How could it be possible to realize that we are not okay with our mathematical model? If you map your x and y on your first quadrant and then draw a curve or a line which will be considered as best fit to your case, then if it happened that the distribution or fluctuation of data points around this best fit is not uniform, the majority of your data are above the line, or the majority of your data is below the line, that means you did not select your mathematical model correctly. If you want to check whether the expected value of epsilon is 0, you have to see your y versus x with best fit or line or curve on top of your data and see if the fluctuation or distribution of your data point around the best fit line or curve is uniform. Some of them are above the line, some of them are below the line, therefore their average or their arithmetic mean is 0. Therefore, in a sense, when we are here, we will try to choose our mathematical model so that this epsilon I has 0 mean automatically. And we are not concerning about a relationship to make it unbiased here. But when it comes to this case, because this formula is unique, as I said, this is the case for every estimator. Your estimated value can be written as a linear combination of computation or observation. Therefore, you will impose unbiasedness condition. But when it comes to this square, in this square, it has to be automatically satisfied, and that has something to do with appropriate selection of your mathematical model. How could it be possible to see if this relation is automatically satisfied, or we have to have a relationship so that if we honor that relationship, then we could argue that the expected value of residual is 0. If we replace residual with its counterpart, and then replace this W hat with linear combination, as this operator expectation is linear operator, we can bring this operator inside, writing it as summation I from 1 to n lambda I expected value of W at S I. And then expected value of this would be the case as well. As you know, W, the stochastic component, is a zero mean random function, which means that this is 0. This is 0. And then you will notice that unbiasedness condition automatically satisfied.
اگر هیچ مدلی ریاضی نبود شما به ازاش ای اپسیلون بشید چی خب در حال این با تیلر کرو انجام میشه و 3000 تا مدل ریاضی داره و منفی هم.
The unfortunate part of the story is that when we want to do a least square problem, we have to honor 4 conditions. And you may ask yourself, if you use table curve or MATLAB or MATCAD or whatever program to go for least square, whether you will honor those four relationship or not. In places like universities, part of our responsibility is to teach these concepts so that the students know what their job is. But when they will refer to professional life, sooner or later they will forget to satisfy those four conditions. Let me talk about those four conditions in a few minutes, where you have to appreciate the properties of this epsilon when it comes to this square. Step 4. Step 5. When it comes to step 5, you have to minimize the variance of residual. But before minimizing the variance of residual, you have to compute the variance of residual. Therefore, step 5 can be devoted to computation of variance of residual. Once again, could it be possible to compare this notion with what we have here? The correspondence, the comparison is 100% one-to-one. What you are really doing here is the same as what you are doing here. Let me first touch on this and then tell you what is this. Your unknown here is going to be A and B, okay? Your unknown here is going to be this coefficient, okay? It means these coefficients here, A and B, behave very similar to these coefficients here. This A and B or this A and B is very similar to what you have here. You have to cast a relationship to obtain A and B here. You have to cast a relationship to obtain lambda I here. How could it be possible to cast that relationship? Here, you will say this epsilon is a random variable in your mind, not in your paper, and the expected value of this epsilon is 0 in advance because you have to choose your mathematical model correctly, and then the variance of this epsilon has to be minimized. If you try to dig further into this variance, the variance of this epsilon, you remember that, let me write it in different color here. If you have a random variable like x, you know for sure that the variance of x can be written as expected value of x2 minus expected value of x to the power of 2. That is our relationship for computation of variance. If you replace this x with epsilon I, you have to write this as expected value of epsilon I to the power of 2 minus expected value of epsilon I, then you have to close this and then raise it to the power of 2. Here we argue that we have to choose our mathematical model correctly so that the expected value of epsilon I is 0. Therefore, this part is 0. When it comes to expected value of epsilon I, we replace it with its discrete formula. And the discrete formula for epsilon, expected value of epsilon is summation epsilon I to the power of 2 divided by n. Out there, where is it? In geostatistics, we will try to minimize this variance. If you look at this, we will try to minimize this because we cannot change n. N is the number of data points. If you want to minimize this variance of epsilon I, that means you have to minimize this epsilon I to the power of 2. Can you try to see what is going on here? In geostatistics, you will try to minimize variance of residual. In this square, you will try to minimize variance of residual again. And here, you will cast your objective function in this way. That is how you will cast your objective function. We will argue that G has 2 degrees of freedom, A and B. You can play with A and B to minimize G or minimize this sum of the square. When it comes to this one, you have to compute this variance first. You have to replace this R with this summation. Minus here you have to find the variance of this first, variance of this second, and then 2 times variance of the first term according to what we have before the holidays, Novus holidays, and then after the Novus holidays, it's going to be a double summation. R of W S I S J. That is the variance of the first step. What is this, Mrs. Rajabzadeh? Covariance of what? If you want to write down the expanded version of this, how you would proceed. If you want to write down the expanded version of this, it's going to be covariance of W at SI and W at ST. That is the expanded version of writing this. Covariance between 2 random variables. And then plus R's of W S0 S0. That is covariance of this, which is variance of W at S0, because the argument is the same. And then minus 2 times I from 1 to n lambda I which is a function of S0, by the way, R sub W S0 SR. Once again, if someone asks you to write down the expanded version of this, it's going to be the covariance between W at S0 and W at SR. 2 random values. Please pay attention. What I wrote here, measure of similarity or measure of variability, could be a function of separation vector or separation distance. How would it be possible to connect that comment to what I have here? If you want to connect that comment to what I have here, the measure of similarity, covariance. Here I wrote it as absolute location, which is a dead end. But I will assume that this R sub W to be a function of separation vector or separation distance. This R is a function of separation vector or separation distance. This R is a function of separation vector or separation distance. It means that if your random function is anisotropic, then you can still use this equation. Because I did not limit myself to separation distance. Here my measure of similarity or measure of variability could be a function of separation vector. How would it be possible to characterize R when it is a function of separation vector? It will become clear later. But for the time being, if this R is a function of separation vector, then we can go ahead as far as we know the numerical or the functional relationship connecting this separation vector to what we have for anisotropic phenomenon. You may want to ask a question here, and this question is very important. Could it be possible for me to play with these covariance if I want to minimize this? Yes or no? No. Because when I am here, I have to characterize my measure of similarity or variability using exploratory spatial data analysis and then background modeling. I have to make it clear at step 1 and step 2 in geostatistical analysis to characterize this covariance function. Therefore, here my degree of freedom for minimization is lambda. Therefore, if I want to replace this variance with its counterpart, I have to write this as, let me use the same notation, no, because I have to use it in some other way, f sub lambda. F sub lambda here is just like G sub A and B out there. Do you remember? Here we have G sub A and B to be summation epsilon I to the power of 2. This objective function here is very similar to what we have here. Here, this objective function has n argument. If you want to minimize this objective function, you have to take partial derivative of f with respect to lambda I, and I has to go from 1 to n, which is the next step. In step 5, our job, our task is to compute the variance of residual. And that is the variance of residual. Step 6. your unconstrained optimization problem. Please pay attention, what do I mean by casting my optimization problem? We have to combine step 4 and step 5 to come up with step 6. Here, the outcome of step 4 is to see that our unbiasedness condition is automatically satisfied. There is no additional relationship here among lambda for honoring the unbiasedness condition. Therefore, if you want to combine step 4 to step 5 to come up with step 6 for your unconstrained optimization problem, here you will argue that your objective function is again the same as this one here, f sub lambda. But later on, when we move to ordinary key regime, you will realize that in ordinary key regime, this expected value would not be automatically satisfied, and you have to have an additional relationship. And then you have to subject your objective function to that constraint for minimization. But for single key regime, there is no additional constraint here relating lambda to what you have here. Could it be possible to say something like what we have in step 6 here to what we have here? Again, here we did not mention any relationship between A and B, but it may happen that you would like to minimize this epsilon I here to the power of 2, and your additional relationship is to have A plus B equal to 1. What happened? You want to minimize this objective function, and you were told that A plus B is equal to 1. Here, it is called constraint optimization problem. مسائل بینیابی مقید این غیرش. If you want to solve this problem, at first you have to make it unconstrained. You have to incorporate this constant into the objective function itself. But for simple regime, there is no such constraint in relating values lambda to each other. What I'm going to cover, I will assume that this objective function is unconstrained, just like what we have here. Later on, when we move to ordinary regime, I will tell you how to solve this problem as well, where you have a constant like A plus B equal to 1. Cast your objective function, which is the same as what you have out there. And then, as I said, and I would like to repeat that again, here we cannot play with this covariance function because we do have it well in advance. At first you will try to obtain experimental covariance function or experimental variogram function, and then you will go for variogram modeling. As soon as you have theoretical variogram at your disposal, then you cannot play with this covariance of variable function anymore. Your degree of freedom here is going to be lambda 1, lambda 2, lambda 3, lambda 4, up to lambda n. You have to play with these lambda in order to make the variance of residual minimized. In step 7, you have to minimize your unconstrained optimization problem. And for this to happen, you have to take partial derivative of f with respect to lambda I, put it equal to 0 for all I from 1 up to n. Now, once again, you will realize that you have to take partial derivative of the first term with respect to lambda I, partial derivative of this with respect to lambda I, and then partial derivative of this with respect to lambda I. Put it equal to 0, and then I has to go from 1 to n. Let me write down partial derivative of f with respect to lambda I equal to 0 for all I from 1 up to n. What would be the partial derivative of this direct summation with respect to lambda I? It's going to be 2 times summation j from 1 to n lambda j arcs of si sj. That's going to be the partial derivative of the first term with respect to lambda I. If you want to check it yourself, you have to expand it, and then instead of having lambda I, you have to take partial derivative with lambda 1, and then lambda 2, and then lambda 3, and see what will happen. This is the partial derivative of this with respect to lambda. The partial derivative of this with respect to lambda is 0, because there is no lambda I in this term. When it comes to this one, the partial derivative of this with respect to lambda I is going to be minus 2 times, and this has to be w si s0 si equal to 0. You can divide both sides by 2. By the way, in your midterm exam, I gave you an exam and a question trying to connect covariance of W with covariance of Y. And you did realize that out there, covariance of W is the same as covariance of Y. Therefore, if R of W at Si Sj is the same as R sub Y at Si Sj, and that is R without any subscript Si Sj, implying that R sub Si Sj is the same as covariance of two random function with W or covariant two random function with Y. Then you can write your Kriging system for simple Kriging as J from 1 to N lambda J, which is a function of S0, times R Si Sj equal to R S0 Sj, Si. As you can see, J is defined internally. You have to define I externally. I is equal to, you have n equation with n elements. If I expand this Kriging system in terms of covariance function, I should write when I is equal to 1, I have R of S1 times lambda 1 plus R of S1 S2 times lambda 2 plus R of S1 Sn times lambda n is equal to R of S0 S1. That is your first equation when I equal to 1. When I equal to 2, R of S2 S1 times lambda 1 plus R of S2 times lambda 2 plus R of S2 Sn times lambda n equal to R of S0 S2. That's your second equation. You can keep going when I is equal to n. R of Sn S1 times lambda 1 plus R of Sn S2 times lambda 2 R of Sn times lambda n equal to R of S0 Sn. You have n equation with n unknowns. You can write it in matrix format. Covariance matrix times vector of unknown is equal to R0. This covariance matrix is basically the coefficient of this lambda here. This lambda is basically what you have as your unknown, and then this vector here is basically what you have here. This relationship is very similar to what we have in least square. Do you remember that? A transpose times A times S, A transpose times 1. This relationship is very similar to what we have out there. You have to solve this system in a step. What is the number? This is a step 7. Test your Kriging system. And then step 8, when it comes to step 8, you have to solve this system for lambda. You have to multiply both sides by R inverse to get numerical value of lambda. In step 9, you have to compute the attributes under consideration at the point which is not sampled. What is that? Why at the point which is not sampled? Because your original problem is this. And this estimated value of y at the point which is not sampled can be written as m plus w hat at the point which is not sampled. And what is w hat? The summation of lambda I which is the function of S0 and W at S0. S0. That is step 9. Once again, I would like to emphasize that even if your original random function is not isotropic, it is anisotropic, which means that your measure of similarity or measure of variability is a function of separation vector, then you are okay. This system is very applicable to both isotropic and anisotropic random function. You may raise a question. Right now, my format of writing is to write R as a function of separation, not even separation vector. I write it as if it is a function of absolute location. If you want to write down this equation as if it is a function of separation vector, then you have to write it as R as a function of 0, because Si minus Si is 0 times round R plus R. Now S1 minus S2 or S2 minus S1, you may want to call this 1, 2 as a vector. This is separation distance, separation vector, times what? Lambda 2 plus R sub H1n times lambda n. And then when it comes on the other side, here you have to write H01. That is how to cast your creating system in terms of separation vector. You can write down the remaining equation just like what you have here. But the point is this. If this is your study area, This is your study area. And this is your data point. And you are asked to estimate the attribute under consideration at the point which is non-sample. What do I mean by H1, 2 as a vector as opposed to as a distance? If you connect S1 to S2, this H1 to here is what you have here. You have to have two arguments to specify also H1, 2. You have to know this distance as well as this angle in order to know the numerical value of R, which means here your covariance function has to be given in terms of two arguments: separation distance as well as the angle that separation distance will make with horizontal axis. Therefore, if you want to rewrite this relationship in a better way to appreciate what is going on, here R sub 0 has to be written as if plus, when it comes to this one, instead of writing this vector, you could write H1, 2 without bar on top of it, and then you have to add eta 1, 2. That is how R is related to separation distance and the angle that this separation distance will make with x-axis times lambda 2. Sure. When your original covariance function is a function of separation vector, you can replace that vector with this. Or, if you want, you can replace that vector with these two. You can write it in polar coordinate system, or you can write it in rectangular coordinate system. These two arguments is for the case when you have rectangular coordinate system, Cartesian coordinate system, and these two is for the case when you have polar coordinate system. Plus, and you have to have a clear picture of vector and angle, just like what we have in finite elements. If this is your S0 and this is your, say, S3, then that's going to be your, it's going to be a 0,3, and this angle is going to be 0,3. What if you have this? How could it be possible to patch on separation distance as well as angle. This is S0n. And then what is the angle? It's quite important to be consistent. What you need to do is to draw a line at this point and then start from here. That's going to be your theta 0, 1. Okay? Theta 0, n. Just like what you have in finite elements, to characterize the angle that separation distance will make with. Counterclockwise. Counterclockwise. This is clockwise. This is counterclockwise. Toward the end of the course, we will talk about anisotropic phenomena. But for the time being, where we are talking about isotropic phenomena, what you need to do is just simply replace this argument with separation distance without angle. Which means that here your measure of similarity or measure of variability is a function of separation distance only. You have to replace this argument with separation distance. And this separation distance would be from here to here only. You have to cast your Kriging system and you have to solve this Kriging system for lambda. That is step 9. Where is the step 9? Here. And then when it comes to step 10, the final step, just like finite element, do additional computation if required. Here, by additional computation, we are exclusively talking about computation of volumes in step 10. Please pay attention. We have 3 types of variance in step 10. Variance of estimated value, variance of true value, and variance of residual. By additional computation, we mean computation of these 3 variances. Variance of estimated value, variance of true value, variance of residual. How could it be possible to compute variance of estimated value? At first, we have to replace this variance of estimated value with what we have here. Where is it? This. And then you will realize that if you have this value added or subtracted from a random variable, its variance would not change. What do I mean? If you have, say, 5, 6, 3, 10, 4 numbers. If you add a constant value to these numbers, say 7, 8, 5, 12, then their variance will not change. Here, if you add this constant value to a random variable, its variance would not change. Therefore, variance of this is the same as variance of W hat. Then you can replace this W hat with its counterpart. And then the variance of this linear combination can be written as a double summation. And then you can simplify this double summation. How? You can simplify this. Please pay attention. Look at this relationship here. This relationship here. The counterpart for this relationship is summation j from 1 to n lambda j r sub si sj equal to r sub s0 sr. This is another version of the same Puget system. How could it be possible to simplify that? What you need to do is to multiply both sides of this equation by lambda I and then take summation. If you multiply both sides by lambda I, take summation, then this double summation can be replaced with what you have out there. It will become summation I from 1 to n lambda I r sub s0 si. That is how to represent the variance of estimated value in terms of coefficient lambda. Remember that we can write this as r lambda dot product r0. Remember? Dot product of this vector and this vector. And then you can replace this by r transpose times r or r transpose times lambda. It has to be a number. This lambda is n by 1. This r is n by 1. And then if you transpose this, it will become 1 by n. This is n by 1. It will become 1 by 1. Here, this r is 1 by n. This is n by 1. Then you multiply them to become 1 by 1, a single number. Can you comment on variance of y? This is 0. What will be variance of y at S0? Look at the assumption that you made below problem statement. I erase it out there. what would be the variance of true value y at S0? Simply as sigma to the power of 2, because it has nothing to do with spatial location. Variance of y at any location is independent of spatial location, be S0 or S or Si, whatever. According to our original problem statement, variance of true value is basically sigma 2. Now, how about variance of residual? Variance of residual, if you remember, we try to cast it as this double summation, lambda I, lambda j, r sub si, sj. This is the first term of variance of residual, plus sigma 2 variance of what? W, which is the same as variance of y, minus 2 times I from 1 to n lambda I r sub S0 S I. Again, we can simplify this. We can replace this by summation of lambda I times r S0 Si. How? Look at this. You have to multiply both sides by lambda I, take summation, and then you will realize that you can replace this double summation by I from 1 to n lambda I r sub S0 Si plus sigma 2 minus 2 times lambda I r sub S0 Si. You can simplify further this relationship, writing it as sigma 2 minus summation I from 1 to n lambda I r sub S0 Si. This is variance of residual. If we want to denote these three variances by a typical notation, we are going to use sigma or simple kriging for this. These R implies that you are talking about residual. This SK implying that your kriging system is simple kriging. Variance of residual is given by this, sigma 2 minus this. And this is variance of true value. And if you want to represent variance of estimated value, perhaps keep it right as if, and sooner or later you will realize that the first property of kriging is very similar from this relationship. Look at how I'm going to interpret the first property of kriging. I can replace this term by variance of estimated value, because as we keep moving, it is variance of estimated value. And then I can write it as sigma r to the sk to the power of 2 is equal to sigma to the power of 2 minus variance of y hat at S0. or variance of estimated value can be written as sigma 2 minus sigma residual to the power of 2. That is interpretation of first property of Kriging. This is variance of estimated value and this is variance of true value at the same point. And here it says variance of estimated value is less than variance of true value. This is called filtering property of Kriging. Kriging will act as a filter. Are you familiar with a filter? In your house, you will put a filter in order to discriminate, filter out the suspended solid in your water supply. Here, this sigma 2 is the variance of true value. See? And here it says variance of estimated value is less than variance of true value. By how much? By variance of residual. Let me put it this way. Variance of true value, estimated value, is less than or equal to variance of true value. Can you interpret this for me? How could it be possible to observe it in your professional life? Variance of estimated value is less than variance of true value. How could it be possible to interpret this in your professional life? Look at this diagram here. In your study area, you have n observation, n stations, and you want to observe this relationship in your study area. How could it be possible to do that? What you need to do in order to get an idea of what this related and equality mean, here in your study area, pretend that you have no observation at this point. Try to use this data to estimate the attribute under consideration at this point. Bring it back to your batch, eliminate this, estimate the attribute under consideration at this point using the remaining data. Repeat this entire process for your n data station. Toward the end of this study, toward the end of this exercise, at every point you have two data. One is what you observe and one is what you estimate. If you prepare histogram for your observation and then compare this histogram with histogram of estimation, your histogram of estimation is much more smoother compared to the histogram of observation. Or if you still want to get a better idea of this relationship, as I said, at every point you have two data. One is what you observe and one is what you estimate. That is what you estimate. That is what you estimate. And then this relationship implies that if you compute the variance of these orange numbers, this number is going to be less than the variance of these white numbers. That's it. Variance of estimated value is less than variance of true value. and I try to simulate estimated value and true value at the same point that I have observation. These are my observation and these are my estimation. Variance of estimation is almost always less than variance of observation. In a sense, Kriging will try to filter out, remove error in your data. This relationship is basically filtering property of Kriging. It is applicable to any kind of Kriging. Ordinary Kriging, universal Kriging, indicator Kriging, fuzzy Kriging, you name it. Any question? The histogram of estimation is much more smoother, less fluctuating compared to histogram of observation. It will filter out your data. It will remove the noise in your data. یعنی fluctuation اون نوسانات رو میگیره. خطا در داده ها رو حذف میکنه. Filtering property of Kriging. On Monday, I'm going to give you a numerical example where we are going to touch on some other properties of Kriging. Filtering property is one basic property of Kriging. Even on Monday, I'm going to tell you how we define 4 PhD students so far touching on network design, based on what we obtained today. How could it be possible to go for network design when you have variance of residual at your disposal? Look at this relationship, variance of residual. Can you tell me, if you want to go for network design, what would be your degree of freedom by just looking at this relationship? Variance of residual will be a function of what? I have for a few minutes, I can comment on this. We have already noticed that lambda is given by R inverse times R0. We did find this lambda. And then we find that variance of residual for simple Kriging can be written as sigma 2 minus, this is lambda dot R0. Sigma 2 minus, you can write this as R transpose times lambda. Just like what I have out there. And then you can replace this sigma 2 minus R transpose, and then you can replace this lambda with what you have here, R inverse times R. Variance of residual. if you dig further into this relationship, you would like to have variance of residual at a particular point to be minimum. What would be your degree of freedom for network design? You cannot play with this because this is constant. What you have to play with is to play with topology. Here, this R transport, this is a vector, and this is a matrix, and this is a vector. If you replace this with a function, this function will be having n, the number of stations, aligned with the topology. Here it is given by sigma 2 minus R0 transpose R inverse times R0. If you want to minimize this variance of residual, you have to choose the number of stations because you have one degree of freedom to be the number of stations, and then their topology, their network, their configuration over the study area, SR, because this has something to do with SR. And then in that case, you can define a variety of objective function because you can change your point under consideration over the study area and then try to see what would be the network topology to minimize the maximum error, as an example, minimax problem. Or freeze the spatial location for S0 because this has something to do with S0. Remember that this is variance of R at S0. And then try to see what would be the network topology to minimize this variance of residual. خب از حوصله همگی سپاسگزار هستم تا روز دوشنبه همگی رو به خدا می‌سپارم.